Alright, we'll get started today. So, it sounds like you're all excited to be back, but we need to get going. So I've been asked by this organization, Alpha Eta Alpha, to post about their upcoming meeting. As I'm told, this is a pre-health organization specifically for non-science majors, so if you fall in that category and you're interested, they have a meeting coming up this week in the Science and Research Building. All right, so then with another reminder, or I guess announcement before we start, the chemistry is the exam review, so if you've totally forgotten about chemistry for the last week, it's time to come back to reality and realize that we have an exam in about 1 week. So the second midterm review, I guess we call them midterms even though there's 3 of them. So the midterm 2 review will be this Friday. So same exact thing as last time, 3 p.m. in the same room. All right, so if you're able to stick around Friday afternoon, please come for that. And I have the problems posted in Blackboard that we'll be going over, same story as last time. And it will be recorded and posted to YouTube and all that stuff, so if you're not able to make it or you want to check it out again afterwards, it will be available for you. So if you haven't signed up for an exam time, do that soon, because I'm sure that the times are becoming more scarce, and especially the desirable ones, and we will have the review Friday. So today we will finish up the material that's going to be on that exam. So what we covered today is still fair game for the exam, and then everything else that we starting on Wednesday will be for the final midterm. So, but today we'll finish up Chapter 6, which is going to be the last stuff that's covered on the second exam. So we've been talking about reactions that happen in solution. We've classified them as acid-base redox reaction or precipitation reactions. We've learned how to balance them and all those things. And now we're going to start talking about stoichiometry for solution reactions. And really this should be, in some sense, a review, at least from the concept standpoint, of what we've been doing in Chapter 5. So you just finished a homework assignment that was all about stoichiometry. And now we're just going to apply those ideas to solution reactions, where there's really only one new thing we have to keep in mind. So from any stoichiometry problem that we've been talking about, moles are the key quantity. So as I always say, when in doubt, convert to moles first. Because when we're using stoichiometric coefficients to relate amounts of reactants and products, those are in terms of moles. So moles are the key quantity, and these molar ratios, as we call them, which come from the coefficients of the balanced reactions, convert one species to another. So when we're doing solution stoichiometry, which is what the topic of this lecture is, and I can't remember, I think your book has it organized where they'll do, they have this sort of sprinkled throughout Chapter 6, but we're going to cover it all in one day to keep it together. But really, solution stoichiometry, no matter what kind of reaction it is, the key idea is just to get into moles first. And the difference here is that we're going to have aqueous solutions that have some molarity defined and some volume, and we're going to use the molarity and the volume to figure out how many moles there are. So it's in this example, if we have 236 milliliters of a 0.524 molar solution, so we want to know how many moles of sodium chloride. So let's say sodium chloride is one of our reactants, and we want to know how many moles there are, which is often going to be the first step in doing these problems, is figuring out the moles of one of the reactants. So we can use the molarity as a conversion factor. So this 0.524 molar, remember, is moles per liter. So that means we have 0.524 moles of NaCl for 1 liter of solution. And what is often going to be a convenient shortcut, although you don't have to do it, is in a lot of solution stoichiometry problems, or the titration things that we're going to see later on today, we're working in milliliters and not liters. Milliliters is a much more convenient unit for laboratory scale work. So what you can do is rewrite this as 0.524 moles per 1,000 milliliters. So this is a shortcut that I'll use a lot just to save a step, because remember that molarity is moles per liter, so our solution volume technically has to be in liters to use the molarity directly, but 1 liter is equivalent to 1,000 milliliters, so you can rewrite the ratio like this if you so desire. So that means in this example here, if we want to find the moles of sodium chloride, we have 236 milliliters of solution, and I'll usually just leave out the word solution, but 236 milliliters of NaCl aqueous solution. And then we use that 0.524 moles per 1,000 milliliters as a conversion factor. So our milliliters cancel out, and so if we multiply the molarity times the volume, we get 0.124 moles. All right, so that's how we're going to use molarity when we're doing stoichiometry problems. It's going to be another type of conversion factor we can use to calculate moles of either a reactant or a product. So now we can then update our stoichiometry flowchart. So we built this a little bit earlier for those mass-to-mass conversions. So let's say we have two species A and B, which are in a chemical reaction. These can be both reactants or one reactant, one product, whatever the case is. So remember that the key part of stoichiometry, which is what we've talked about in Chapter 5 a lot, is that if we have the moles of one species in a chemical reaction, we can calculate the moles of something else that's involved in that reaction using the reaction coefficients as ratios. So that's still the key linchpin here, is getting into moles of one species, calculating moles of another species by using those coefficients from the balanced reaction. What we saw before when we were doing stoichiometry problems in Chapter 5 is that the most common quantity to relate to moles was mass. So if we have the mass of one species, we can use the molar mass to calculate moles. And we can do the same thing for the other species, B. So for reactions that happen in the solid state, for example, if we want to just weigh out the masses of reactants, we can relate those to the moles. And then we also saw something else that we can do that's kind of cute but not particularly practical, is we can calculate the particles, as we'll call it, of A, which would be the atoms, molecules, or ions of A, whatever A's identity is, and that's where we use Avogadro's number. And we can do the same thing for B. So we've already seen that a little bit. It's not particularly practical, so you're not going to go into the lab and measure out, 5 point whatever times 10 to the 24th molecules of something. That's just impractical. But you can calculate how many molecules or atoms are involved for a given species using Avogadro's number. So that's something we've already known how to do. And then really the only thing we're adding now when we're doing solution stoichiometry, as we introduced on the last slide, was that if we have an aqueous solution of A with some volume, we can relate that to the moles of A using the molarity. And we can do the same thing for the other species B. If we have a volume of an aqueous solution of that component, we can use the molarity to relate the moles of B to that volume. So we're just adding one additional layer to our chart here, and then in Chapter 8, I think it is, we'll add one more involving gases. But really, we're just building up the number of ways that we can calculate moles, but the concept is still the same. We have to get into moles and then use reaction coefficients to convert between them. All right, so that's what we're going to be adding today. So then let's just see how this works for a bunch of example reactions. So we'll start with a precipitation reaction. So let's say we want to know what is the identity and mass of the precipitate that is formed when excess calcium chloride reacts with 250 milliliters of 0.0555 molar silver nitrate. So one thing that we saw in the last homework assignment, and that is especially going to be true when we're dealing with stoichiometry problems related to aqueous solution reactions, is that we have to be able to write the balanced reaction first. If we don't have a balanced chemical equation, then we're hopeless in terms of doing anything with stoichiometry. So this is a precipitation reaction. So to review how we write those out, we're telling you that we're forming a precipitate, so that should automatically, a bell should go off in our head that says this is precipitation reaction. So we have calcium chloride. Okay, calcium chloride is soluble, so we write it as an aqueous species. We're reacting that with silver nitrate. also soluble because it's a nitrate. And then remember that the products of a precipitation reaction, we're just going to exchange the ions with each other. So the calcium 2 plus is going to be paired with the nitrate NO3 minus in the product. So one of our products is going to be calcium nitrate, which has to have 2 nitrates to balance the charge. And that's still going to be soluble because all nitrate salts are soluble. And then the other species is going to be the chloride, the anion from the first ionic compound pairing with the cation silver plus from the second. So that's going to be AgCl. Remember, these silver lead halides, these are sort of dead giveaways. These are going to be the precipitate. So silver chloride is the precipitate. That was sort of the first part of this, is identify what the precipitate is. That's the insoluble species. Now we're not quite done yet. We have to balance this. So if we have 2 chlorides in calcium chloride, we need to have 2 silver chlorides, and then we need to have 2 silver nitrates to balance that. So usually coefficients for precipitation and acid-base reactions are pretty simple, 1s, 2s, and 3s for the most part. But we have to add a couple to balance this out. And that's going to be important then when we do the stoichiometry calculation in a little bit. We could also, if we wanted to, write a net ionic equation for this. So we learn how to do that as well. So the net ionic equation is going to be, we have silver plus combining with Cl minus to make our precipitates. Remember that the net ionic equation involves the ions that are combining to make our precipitate, so Ag plus Cl minus, and the coefficients reduced down to 1 to 1 to 1. So we could write the reaction like this, but I guess what I'll tell you now is that it's usually the formula or the molecular equation that's going to be more convenient for doing stoichiometry problems. So we learned how to write net ionic equations, and that's something you'll have to do on your own on the exam and on the homework assignment this week. But if you're doing a stoichiometry problem, I would say don't bother going all the way to the net ionic equation. So usually just this equation up here, what we call the formula equation that just has all the species intact, that's going to be the most convenient representation to use for the stoichiometry problem. All right, so I would say don't bother going through the steps to generate the net ionic equation if all you have to do is just some sort of stoichiometry calculation. Okay, but we have a balanced reaction now, and I mean, either of these could work for doing the stoichiometry problem. We don't have to use one or the other, but like I said, it's more convenient to just probably use this one. Now that we have the balanced reaction, we can then do the calculations to figure out what the question is asking, which is the mass of precipitate, the mass of silver chloride that's going to form. All right, so we'll have to rewrite our balanced reaction because we can't do anything without that. So we're going to, in the second step now, we have a balanced reaction. We'll determine the mass of the precipitate, which is AgCl. All right, so again, the reaction is calcium chloride plus 2 silver nitrates gives us calcium nitrate. Those are both spectator ions, calcium 2 plus and NO2 minus. And then our precipitate, silver chloride, 2 equivalents. All right, and we have excess calcium chloride, so we only have the amount for one reactant, so we don't have to worry about figuring out which of these is the limiting reactant. It's just excess calcium chloride, so we're going to start with the amount of silver nitrate. So we're going to calculate the grams of silver chloride. We're starting with 250 milliliters of silver nitrate solution. And then, as I said, as I've introduced, we can use the molarity to figure out how many moles of silver nitrate there are. So the molarity of silver nitrate is 0.0555 molar, so we have 0.0555 moles of silver nitrate per 1,000 milliliters. So again, that's that shortcut I'm going to use instead of having to convert everything into liters all the time. So we now have moles of silver nitrate. We can use coefficients from the balanced reaction. So we're looking for the amount of silver chloride that forms. So if we look at the balanced reaction, we have 2 moles of silver chloride. We have the coefficient of 2 here, and that's per 2 moles of AgNO3. So So these react in a 2:2 or 1:1 ratio, so we don't have to even really do anything here, but this cancels out moles of silver nitrate, converts into moles of silver chloride, and then the last step, we're looking for the mass of silver chloride, AgCl, so we have to use its molar mass to convert the moles back into the mass. All right, so here we need the molar mass of AgCl. If you go to the periodic table and just add them up, so we need this molecular weight or molar mass for silver chloride. The atomic mass for silver is 107.9. The atomic mass for chlorine is 35.45. We add those together and get 143.4. So that's the molar mass of silver chloride. We multiply by that, 143.4 grams of silver chloride per 1 mole. So that cancels out moles, converts into grams, and we get 1.99 grams of silver chloride. All right, so most of these steps are very similar to what we've done before with stoichiometry. The only difference here is we're starting with a volume of an aqueous solution and using molarity to figure out the moles as our first step. Okay, any questions on that? All right, so then the next thing we'll do is very similar, but this is going to be a solution stoichiometry problem that involves a limiting reactant. So in this case, we're taking sodium sulfide, 125 milliliters of a 0.25 molar solution, and we're combining it with 95 milliliters of a 0.45 molar solution of lead nitrate. We want to know what is the mass of the precipitate that forms. All right, so again, we need to write the balanced equation. We're not giving that to you here, so this will be a good review for precipitation reactions. So we're taking sodium sulfide, Na2S, combining that with lead nitrate. So the two products are going to be sodium paired with nitrate. Sodium nitrate. All right, that should be an obvious soluble compound. It has sodium and nitrate in it. Both of those are always soluble. And then the other product is lead sulfide. Most sulfides are insoluble. Most lead compounds are insoluble, as it turns out. So this is obviously going to be our precipitate. It's lead 2 plus combining with S2 minus, so it's just going to be PBS. So we have to again have a couple of coefficients, or just one coefficient to balance this here. So we have 2 sodiums. We added 2 there on the product side to balance sodium, and then I think everything else falls into place. So just one coefficient here, everything else is a 1. So that's our balanced chemical equation. Now in this problem here, so we're going to end up looking for then the mass of this product here. That's the mass of precipitate that's going to form. But in this case, we give you the volumes and the molarities for both reactants. We have the volume and the molarity for sodium sulfide, and we have the volume and the molarity for lead nitrate. And just like any stoichiometry problem, if we give you amounts for 2 or more reactants, the first thing you have to do is figure out which one the limiting reactant is. Because any other calculation that we do is going to start with the limiting reactant. So we have to take both of these quantities here, both of these pieces of given information, and figure out the limiting reactant. So that's going to be our second step here, is determining the limiting reactant. And there's no difference here. Remember that for determining the limiting reactant, we find the moles of each reactant, and then we divide it by the coefficient in the balanced equation. So the moles of sodium sulfide, we have 125 milliliters of that solution. That's just from the given information. The molarity is 0.25 molar, so it's 0.250 moles per 1,000 milliliters. And we'll stop here for now because that's going to give us the moles of that reactant, 0.0312. And then the stoichiometric ratio, this R as we defined it, is just that number divided by the coefficient. The coefficient for sodium sulfide is 1, so its stoichiometric ratio is the same number. All right, so that's the stoichiometric ratio for the first reactant. We do the same thing for the lead nitrate. We take its volume, which is 95 milliliters. We use the molarity, which is 0.45 molar. And that's per 1,000 milliliters or 1 liter. And so we get 0.0428 moles of PbNO3. Oops, I didn't write that right. Alright, so that's the moles of lead nitrate, and then the stoichiometric ratio for lead nitrate is just that number divided by the coefficient. The coefficient for lead nitrate is also 1, so we don't even have to divide it by anything, it's just 1. So, alright, so we see that this is the smaller number. Sorry, this number here is the important one, the stoichiometric ratio. That's the smallest number, so this is going to be the limiting reactant. Alright, so we have to find limiting reactant first. This is the way that I like to do it. But remember, once we find limiting reactant, all of our calculations start with there. So then the last step in this problem is going to be do the calculation. And remember, anytime we're doing a stoichiometry problem where limiting reactant is important, you have to start with limiting reactant in your calculation. So we're looking for the mass of lead sulfide that forms, that's our precipitate. We've already calculated the moles of our limiting reactant, so we can just start with that amount. So up here we found that there's 0.0312 moles of sodium sulfate, which we then determined was the limiting reactant. So we don't have to go back to all the way to the beginning. We can start with that intermediate calculation, 0.312 moles of sodium sulfate. We look at the balanced chemical equation. 1 mole of lead sulfide forms for every 1 mole of sodium sulfate. Sulfide, not sulfate. 1 mole of lead sulfide forms for every 1 mole of sodium sulfide, so it's a 1-to-1 ratio. One mole of PBS for every mole of sodium sulfide. Then we're looking for the mass of lead sulfide. So here we're giving you the molecular mass, or the molecular weight of lead sulfide is 239.3. So we convert moles back into grams, and we get 7.47 grams. All right. So it's just a limiting reaction problem, something we've seen now for a while, and the only difference is that we have to use molarities and volumes to calculate the moles of each reactant as opposed to masses like we did before. All right. So as long as we understand the concept of how to approach these problems, we're really just adding one additional step here, which is using molarity. So any questions on that before I move on? All right, so the next topic we're going to talk about, which is very much related, is titration. And usually the word titration elicits a collective groan from students. But I want to try to convince you guys that really a titration is just a solution stoichiometry problem. So if you understand everything we just did, about solution stoichiometry using molarities and volumes to calculate moles, that's all we're doing for titration also. Now, it has a fancy name because what we're doing operationally in a titration is we're using a solution of a known concentration to determine an unknown concentration of something else. So when we're doing a titration, we're mixing two solutions together, and one of those solutions we know the concentration already. Doesn't really work if both of your solutions have unknown concentrations. But we use a solution of known concentration going to use that to determine the concentration of an unknown solution, or an unknown concentration. Now there's some variations on this theme, but that's the essence of what we're doing in titration. We have two solutions that we mix together. So the apparatus, if you've done it in the lab already, or you will in the future, you have a solution down here and you're adding another solution from what's called a burette, and you can then measure the volume of the solution that you add. So that's going to be sort of the key measured quantity. So there are many different types of titrations, but the most common ones that we'll talk about are acid-base titrations. And probably the ones that you would most likely do in a chemistry lab. So in this case, a solution of base is added to acid, or vice versa. So we're mixing two solutions together that are going to react with each other. One of the nice things about titration problems is that in almost every case, all we really care about are the two reactants that are reacting with each other. We don't really care about what the products are or what the full balance reaction is. As long as we know the two reactants and the ratio that they react with each other, that's really all we need to know. And an acid-base titration is going to be the most common one. Another definition to be aware of is the equivalence or endpoint. So this is really what we're trying to strive for in a titration experiment. It's the point at which the moles of hydroxide that we've added, so we're mixing an acid and a base. The base has hydroxide, the acid has H+. So the moles of OH- that we've added, or the moles of H+ that we've added if we're doing an acid into a base, is going to equal the moles of H+, or OH- that we started with. Alright, so that's the whole idea with that titration, is we have one reactant down here, we're adding another reactant, we're going to add just the right amount of that reactant until they've completely reacted with each other. That's what we call the equivalence point, or the end point. And in an acid-base titration, that means the moles of H+ that we've added equals the moles of OH- that were initially present, or vice versa, depending on which way we're doing the titration. So the equivalence point is the point where we've completely neutralized the solution, where all of the OH- and all of the H+ have reacted with each other. And the way that we can tell when we're at the equivalence point is with an indicator. And this is some additive that we put in the solution, some small amount of something that changes color at the equivalence point. And we don't have to worry too much about how that happens. You'll deal more with that in chemistry too. But there's something else that's in here, and you can kind of see it up here. There's this little bit of a pink color. So usually the indicator that you use for acid-base titrations, it turns pink once you've gotten to the end point. And so that's what we're doing here. We're just adding just the right amount of the second solution to the first solution that they completely have reacted with each other, and that's what we're trying to get to in a titration. Okay, so let's see examples of titration problems, and really, like I said, these are just stoichiometry problems, nothing different than that. So we want to know how many milliliters of 0.126 molar sodium hydroxide solution are needed to neutralize 52.3 milliliters of 0.297 molar H2SO4. All right, so this is an acid-base titration. We're adding a base to an acid, and we want to know how much of this base do we have to add to completely neutralize. Remember that neutralize means we've gotten to the end point, we've gotten to the point where all of the acid has reacted with the base. So just like any stoichiometry problem, for a titration problem, we need to have a balanced reaction, or at least a reaction where we know the ratios of the two reactants. So to review how we write equations for acid-base reactions, we have our base plus our acid. Now the nice thing is, as I said, for a titration problem, we don't really care what the products are, because all we're interested in is the ratio of the two reactants that we're adding in. But if we want to write the products out for this reaction, remember that in an acid-base reaction we form an ionic compound. So the sodium from NaOH pairs with the sulfate SO4 2- to make sodium sulfate. And then the other product of the acid-base reaction is always water. Sorry, I'm going to move that over a little bit. And like I said, the important part to balance is the left side of the equation. So our base has 1 OH minus. Our acid has 2 H pluses. These need to react in an equal ratio, so we need to have 2 NaOHs to react completely with H2SO4. So now we have 2 OH minuses reacting with 2 H pluses, so we put a coefficient of 2 in front of NaOH. That also gives us a coefficient of 2 in front of water, but like I said, we don't really care about that. So this is the full balanced equation, but the important part is to realize that our base, which only has 1 hydroxide, reacts in a 2-to-1 ratio with our acid, which has 2 H pluses. Okay, so that's the first step. And now we're just going to do a series of calculations to find out what the question is asking for. So we're looking for how many milliliters of NaOH solution, and we can do this all in one string of steps if we so desire. So we know that we're reacting this with 52.3 milliliters of the sulfuric acid solution. So when we start the calculation for our titration problem, we're always going to start with the species where we know the volume and the molarity. So for sulfuric acid, we know that we have 52.3 milliliters, and we know the molarity is 0.297. So we're going to use that to calculate the moles of sulfuric acid. And the molarity is 0.297 molar, so that's going to be 0.297 moles per 1,000 milliliters. We know that we've now calculated the moles of H2SO4, and from the balanced chemical reaction, balanced chemical equation, we can then figure out how many moles of NaOH that corresponds to. So for every mole of H2SO4, we react 2 moles of NaOH. So there's a coefficient of 2 in front of NaOH, and a coefficient of 1 in front of H2SO4. All right, now if we look at what the question is asking us, we're looking for the volume, the number of milliliters of NaOH solution. And now we're going to sort of work backwards. We have the number of moles. We can use the molarity then to find what the volume is. So we have the molarity of the sodium hydroxide solution. So we know that there is 0.126 moles of sodium hydroxide for every 1,000 milliliters, or every 1 liter. And so what we can then do is we want moles to cancel out, so we put that in the denominator. We're going to divide by the molarity in this case. So moles of NaOH cancels out. That's per 1,000 milliliters, or 1 liter if you want to do it in 2 steps. And that gets us into the desired quantity, which is milliliters of NaOH solution. So when we multiply all these out, we get 247 milliliters. All right, so it's just a stoichiometry problem, but again, the one new thing we've introduced is using molarity to convert between volume and moles. And so here we didn't even need molar masses or anything. We just used the volume and molarity of H2SO4 to figure out how many moles of that were. We used the coefficients from the balanced reactions, to the 2 and the 1, to find out how many moles of NaOH there are, and then we use that number of moles to convert back into a volume using the given molarity. All right, so we know that this is going to require 247 milliliters of NaOH solution. Okay? Yep. Well, it impacts the stoichiometry, so that's why they react in a 2-to-1 ratio. So there are 2 H pluses that's associated from H2SO4. When we just tell you that the molarity of H2SO4 is 0.297 molar, that's the molarity of the entire species H2SO4. So the molarity of H plus would be twice that amount. It would be 0.595 or whatever. But all that really impacts for the purpose of this problem is just that they react in a 2-to-1 ratio. It doesn't really impact anything else beyond that. So it is important to keep in mind how many protons your acid has and how many hydroxides your base has, because that's going to influence the ratio in which they react with each other, which is then going to be determined in this step here where we're converting between them. We have to use the correct ratio. Okay? All right, any other questions? All right, we can move on to see another example here. And this is, in this situation, we're looking for the molarity of the NaOH solution. So we're taking a solid acid, which has one acidic proton, and then we're going to take 1.25 grams of that acid, and we're going to titrate it with NaOH solution. We find that 56.3 milliliters of that solution are required to reach the endpoint. And we want to know what is the concentration of NaOH solution. So another application of titration, as I said, is to figure out the unknown concentration for a solution. So we don't know what the molarity of NaOH is, but that's what we're going to try to determine using this information. So we're looking for the molarity of NaOH. So it's always helpful to think about what is the question asking us, and then figure out what piece of information we need to extract from that. So we need the moles of NaOH, and we need the liters of solution. If we look at the given information, we know what volume of NaOH solution we use in the titration in milliliters. We can easily convert that to liters. So we pretty much already have the volume part, but we need to calculate how many moles of NaOH are in that solution. And that's where we use the data. So the balanced reaction, again, is going to be KHP, is the abbreviation for our acid, plus NaOH. And we form whatever the salt is of KHP. I don't even know what that would be called. KHP minus, and then we're forming H2O. Now the key point here, without even writing out the full reaction, is that this has one H plus, NaOH has one OH minus, so they're going to react in a 1-to-1 ratio. So we don't have to worry about any coefficients here, because we're going to have 1 mole of KHP reacting with 1 mole of NaOH. If our acid has one acidic proton and our base has one OH minus, they're going to combine in a 1-to-1 ratio. So then if we want to find the moles of NaOH, we're going to use the information from the problem to do that, because that's the other piece that we need to calculate the molarity. So the moles of NaOH, we have our acid was added as a solid in this case, 1.25 grams. We can convert that into moles using the molar mass. So here we're going to kind of combine the two approaches that we've used for stoichiometry before. So we're given the molar mass of KHP is 204.22. So we divide by the molar mass to get the moles of KHP. We know that the acid and the base react in a 1-to-1 ratio, as we determined here. So there's going to be 1 mole of NaOH present for every 1 mole of KHP that reacts. And that gives us the moles of NaOH is 0.00612. Okay, so that's the moles of NaOH. We now also need the liters of solution, which is not directly given to us, but we're given the milliliters of the NaOH solution that we added. So we have the liters of our NaOH solution is going to be 56.3 milliliters. Then we just have to convert that into liters. So 1 liter of NaOH solution has 1,000 milliliters. So we have 0.0563 liters. So we have moles of NaOH, we have liters of solution, and now we can just divide the two to get the molarity, which is what the question is asking us for. Alright, so I have more space for work here, but all we have is one step left, which is going to be the molarity of our NaOH solution is going to be the moles that we just calculated, 0.00612 moles, divided by the liters of solution, which is given, and we had to convert that from milliliters into liters. And we get 0.109 molar. Alright, so if we're asked to find the molarity of a solution, we have to find the moles and the liters, and usually, in this case, as we saw, the volume is going to be given to us, and we have to use the titration information, the amount of acid that we had present, to figure out the moles of the base that are present. Okay, questions on that one? Alright, let's just keep plugging along here. So I think I'm going to skip this one because it's almost identical. And I'm running out of time. So let's do the last two here because these are a little bit different. I'll put that one in the notes before I post them so you'll be able to see it. But let's start with this one here. So as I said, in titration problems, a lot of what we're doing is finding unknown concentrations. So that's the example I just did. And the one that I skipped is also really the same theme. But we can also use them to find unknown molar masses. So here we have, and this was a lab that I did when I was a graduate student TA. So this you might see something like this in your future chemistry labs if you take them. So we have an unknown amino acid which has one acidic proton, was dissolved in water. This was titrated with 0.125 molar NaOH solution, and we found that 27.1 milliliters were required to reach the endpoint. What is the molar mass of the unknown amino acid? All right, so as I said, the way to approach these sort of long-winded problems is to go to the end of the question and see what it's asking for. So we want the molar mass, which is grams per mole of the unknown amino acid. So if we want the molecular weight of the molar mass, we need the mass of the unknown, and we need the moles of the unknown. So those are the two quantities we need to be able to calculate this. If we look at the information in the problem, we know that we're starting with 0.254 grams of our unknown, so that's given to us. And so now we just need to calculate the moles of HX using the titration information. All right? So the moles of HX, we should keep in mind that these react in a 1-to-1 ratio because if it's abbreviated HX, that means it has one acidic proton, and that's going to then react with NaOH in a 1-to-1 ratio. All right, but the important part is, again, this 1-to-1 stoichiometric ratio for the acid and the base. So if we want to find the moles of HX, we know that we use 27.1 milliliters of our NaOH solution. So we have 27 milliliters of our base. The molarity of our NaOH, we know in this case, is 0.125 molar. So we have 0.125 moles of NaOH per 1,000 milliliters. And then finally, we know that they react in a 1-to-1 ratio, so we have 1 mole of HX present for every 1 mole of NaOH that reacts. And so when we calculate this out, we find that there are 0.0339, sorry, 00, I think I missed a 0 there. That's how many moles of our unknown acid must be present. So we know that there are that many moles of NaOH. They react in a 1-to-1 ratio, so that's how many moles of HX, the unknown amino acid, were initially present. And then finally, to find the molar mass, the molecular weight, we just have to divide those two quantities. So the mass was given to us, 0.254 grams. From the titration, we found that corresponds to 0.00339 moles. That gives us 74.9 grams per mole. All right, so this is how we can use titration to find an unknown molar mass. And again, if we know the definition of molar mass, which is grams per mole, we can use the stoichiometry to find the moles, and then we just divide the mass by that number and get molar mass. All right, so this is just another application of really the same type of calculations using molarities and volumes and stoichiometric ratios to calculate the amount of moles that are involved in an aqueous reaction. All right, the last one I'll do is really similar to this, but here we're going to do what's called a redox titration. So as I said, most titrations that we do are acid-base, but we can also do what's known as a redox titration. So let's say we want to bleach our hair, if that's the thing that people still do. I know back in the 90s it was a big thing. So it's the active ingredient is hydrogen peroxide, H2O2, and we want to know the amount of H2O2 in 14.8 grams of hair bleach, and we want to find out what is the mass percent of H2O2 in that sample of hair bleach. So we took 14.8 grams of the bleach, titrated it with potassium permanganate, and we found that we required 43.2 milliliters to reach the endpoint. So I'm giving you the balanced reaction here. So really what we're doing is we're taking MnO4 minus, which is highly colored, we're titrating it with H2O2, the color disappears as it converts to Mn2+, and as soon as we've added just enough MnO4 minus, the pink color of the permanganate will persist. So this is a redox titration where we don't even need an indicator because one of our reactants is highly colored. Those are details you don't really need to worry about, but what we're looking for here in this problem is the mass percent of H2O2. So what we need is the mass of H2O2 in grams divided by the mass of our hair bleach in the same unit, and we multiply that by 100. Alright, so we're told that we're starting with 14.8 grams of our hair bleach solution, so that's going to be our denominator that's given to us. And now we just need to use the titration data to figure out how many grams of hydrogen peroxide are actually in there, because hair bleach, again, is a solution that has hydrogen peroxide, probably a lot of water, probably some things to make it smell nice, and all kinds of other stuff in it. But we just want to know how much H2O2 is in there, and that's what the titration will tell us. So if we want to find the mass of H2O2, it's a very similar set of calculations that we've been doing. So we know that the volume of the titrant that was required, 43.2 milliliters of the KMnO4 solution. We know the molarity of that is 0.105 molar. So there's 0.105 moles of KMnO4 for every 1,000 milliliters of that solution. Now the balanced reaction is given to us in terms of MnO4 minus. So if we want to write this out explicitly, we can realize that there are 1 mole of MnO4 minus for every 1 mole of KMnO4. All right, that's that may be obvious just by looking at it, but the balanced reaction is just given to us as an ionic equation, so we should recognize that there's 1 mole of MnO4 minus per moles of KMnO4, because that's what we're technically adding, but it's KMnO4, only one ion there. Then we use the stoichiometric ratios to find out how many moles of H2O2 that corresponds to. So we found the moles of MnO4 minus, how much H2O2 is that reacting with. The ratio is 5 to 2, so we have 5 moles of H2O2 for every 2 moles of MnO4 minus that react. So MnO4 minus, we convert that into H2O2. Now what we want for this calculation up here is the mass of H2O2, so we can use the molar mass, which is 34.02, to calculate the mass. So 34.02 grams of H2O2 per 1 mole. And so we get 0.386 grams of H2O2. So we put that up here in into our mass percent formula, and we get 2.61%. So that's the percent by mass of hydrogen peroxide in that sample of hair bleach. Alright, so the series of steps are very similar to what we saw before. This is just a redox reaction instead of acid-base, and here we had to calculate mass, so we had this last step here. So practice those over and over again until you get good at them, and please come to me with any questions you have in the next week or so.